Let us continue our study of bifurcation. This time, let's look at pitchfork bifurcation. All right. Pitchfork bifurcation usually occurs when you have a physical system with symmetry. All right. And I'm not going to delve into particular examples. I'm going to address that in another video, or if you're in a class, I'll probably give you that as a homework. And another property or characteristic of pitchfork bifurcation is that fixed points appear and disappear in symmetric pairs. All right? Fixed points appear and then disappear in symmetric pairs. And this could also be disappear and then appear. All right, there are two types of pitchfork bifurcations. And the first one is supercritical. That's the easier one to deal with. I always want to look at this supercritical as two words. I don't know why, but it should be one word. Supercritical pitchfork bifurcation. And then another one is the subcritical. Subcritical. Pitchfork bifurcation. All right, let's start with the supercritical. Pitchfork bifurcation. All right. For the pitchfork bifurcation, the normal form, which we can think of as the general form, is ax dot is equal to ax minus bx cubed, where b is greater than 0. A and b are constants. Also, another way of thinking of this in certain textbooks, including the Strogatz that we're using, they just reduce the pitchfork bifurcation normal form to x dot is equal to maybe ax minus bx cubed. So if you minus x cubed. So if you divide through by b, maybe to find a fixed point, divide through by b, when you set the right hand side equal to 0, and then change a over b to a, you get the same thing. So let's do an example. Example 1. I liked the color I had before. I don't like this dark. I don't like this warm blue. Example 1. Let's discuss the bifurcation for x dot is equal to rx minus x cubed. Okay, so let's look at if you sketch this diagram, or if you sketch x dot against x, let's see, this is the x dot and this is x. No. Okay, so how about I know I'm going to be doing 3 of this, so let me just copy and paste 3 times before I mess it up. Paste again. Yeah. Okay. So what am I saying? If I have, let's think of when R is 1, for instance. If R is 1, then we have if R is 1, I'm going to do some very rough work over here. Let me do it in green. If R is 1, we have x dot is equal to x minus x cubed, and then we're going to set it equal to 0, and then we have x minus 1 minus x squared. So we just get x is equal to 0, x is equal to 1, and x is equal to -1. All right. So why am I doing this? I'm doing this because I want to look at the different fixed points for different values of R. So we have a fixed point of 0. I'm assuming that R is equal to 1. So, and this will apply when R is greater than 0. Maybe I should do it here. Let me do R greater than 0 over here. So I can do R less than 0 over there. So this would be for, let me reserve this for R less than 0. R greater than 0, I have a fixed point of 0. I have a fixed point at 1. I have another fixed point at -1. So I did this here I just chose R being equal to 1. Because R is greater than 0. I use 1 as an example. I'm not going to erase this. So if I sketch for R greater than 0, I am going to get something like this. Oh no. Why would I do that? Why would you do that? Be nice to me. All right. So this is a type of graph you're going to get. So this is, let's do red, going this way, and coming that way, going this way, coming that way. So this is definitely stable. I'm going to use red, even though red, well, let me not use red. Let me use green for stable. This is stable, and this is unstable, okay? So now, if R is less than 0, if R is less than 0, you're actually going to, let's say R is -1. Think of what we get. We end up with -x minus x cubed. If I factor out -x, I'll end up with 1 plus x squared. All right? So if I set this equal to 0, my only fixed point will be x is equal to 0. And then we have x is equal to plus or minus I, right? So the only real valued fixed point is x is equal to 0, or x is equal to 0. And we get something like that, right? And it is stable. It is stable. All right, now when x is equal to 0, we just have -x cubed. So we have something like this. Okay. It is also stable. It's weakly stable. But if you notice, it will start at 0, it will start to lose its stability. When R is 0, it will start to lose its stability. So let's see. Let's do this. Make it more like that. So we have that, and it's still stable. Okay. So this is when r is equal to 0. Okay. So we can sketch the bifurcation diagram, but for now we can see that bifurcation occurs when r is equal to 0, right? And this is one thing we note. Another note is that a bifurcation point is r equal to 0. Okay, so, and then to sketch the bifurcation diagram, all we need to do is solve for we start by solving for the fixed point. The fixed point is just to set the left-hand side equal to 0. If you do that, or the right-hand side, if you do that, you end up with x, then r minus x squared is equal to 0, which will give you that x is equal to 0 is one fixed point, and another fixed point is going to be x is equal to plus or minus square root of r. All right, and I feel like we've seen something like this before. I'll let you think about where we saw it if you are taking the class. But if you sketch the fixed point, let's sketch r against x star. So we have this. Okay, this is our r axis, and then x star is this axis. So we have when r is less than 0, x star, this is the x star axis. All right, I'm gonna do our bifurcation in black. All right, so this is the x star axis. Let me backtrack. When x star is equal to 0, we're on the r axis, right? So, and when x star is equal to 0, we have that the fixed point x star equals 0. That's what I meant to say. The fixed point x star is equal to 0 is stable until we get to when r is 0. It's stable for r less than 0, and then it becomes unstable. See, it becomes unstable. So let's do unstable with dotted lines. Okay, and then what happens? We now get x star, the fixed point x star equals square root of r, plus or minus square root of r, becomes stable, or they emerge, they appear once r is greater than 0. They start appearing at r equal to 0. So we have, oh, no, we don't want that. Let's do black. So we have this, and then we have that. So that's our bifurcation diagram, okay? And you can see why it's called pitchfork bifurcation. And this is a supercritical pitchfork bifurcation, so that you have a stable fixed point that bifurcates into two stable fixed points. That's the pitchfork bifurcation. All right, so that's example 1. I would want you to try, I would like you to try this next example by yourself. Oh, that's large. Hold on. Example 2. I want you to discuss the bifurcation of x dot negative x plus beta hyperbolic tangent of x. So if you're not familiar with this function, with hyperbolic tangent, I would like you to look it up first. Study this function a little bit. So the only the bifurcation parameter is beta, okay? And you're going to get a supercritical pitchfork bifurcation. All right. So let's see. What else can I say about this? I want to say more, but I don't want to inundate you with a bunch of things. All right, so let's look at some properties of no, I don't like that. Properties of the subcritical pitchfork bifurcation. We can really go in depth with this, but I would like to just explain it in terms of diagram. Okay, so this is invariant under the change from x to negative x. All right, x to negative x. So what does that mean? That means that if we have, let's look at the normal form. Let's say we have x dot is equal to ax minus b x cube. Now if we replace x with negative x, we end up with negative, take the derivative of negative x, you get negative x dot is equal to a times negative x minus b times negative x cubed. All right, and this will give you negative x is equal to minus ax, then plus bx cubed. And this will now give you, if you divide through by -1, you get, this is x dot, you get x dot is equal to ax minus bx cubed. So you get the same thing. So going from from positive x to negative x doesn't change a lot. It doesn't change anything, in fact. So that means this is another way of demonstrating the symmetry preserving nature of pitchfork supercritical pitchfork bifurcation. All right. Okay, so let us look at another example. I would like us to look at, let's call it, I'm going to call it example 3. We're going to stay with the example I solved, example 1. So this example is to plot the potential V of x for the system x dot is equal to rx minus x cube for cases r less than 0, r equal to 0, and r greater than 0. Okay? All right. So remember, so we have x dot is equal to rx minus x cube, and we can think of it as x dot is equal to f of x. And for the potential, to get our potential V, We get it by setting the f of x equals negative dv dx. All right. So this means that we can get our v as or let's say negative dv dx. So our negative dv dx is equal to rx minus x cubed, which means that dv dx is equal to negative rx plus x cubed, which means that v is the integral of rx minus x cubed dx. All right, which means that v of x is equal to negative 1/2 rx plus 1/4 x to the fourth. Okay, you can use Maple to sketch this. You can sketch it by hand. You can do it however you want. But pick values. If you pick values for r, just pick one value. Let's say you pick r equals 1, and you pick r less than 1, and you pick r equals, let's say you pick r equals 1. What am I saying? I should think more when I talk. R equals 1, r equals 0, and r equals negative 1. Let's see what you get. So remember that potential is another way of finding out if fixed point or showing fixed point and discussing their stability. So for r less than 0, if you sketch this, this is what you get. You get something like this. For r equal to 0, if you sketch your function, this is the function v here. If you sketch the function v, this start becoming a little bit flatter than when r is less than 0. So this is r equal to 0. And then when you sketch r, for r greater than 0, you have that. You have something like that for r greater than 0. Okay, so remember when we discussed potential, we said that if you have a fixed point that lives in a minimum, right? Because these are fixed points, right? So that lives that correspond to a minimum, another way of saying it, then that fixed point is stable. This is stable, and this would be an unstable fixed point. So this is still stable. This is beginning to lose its stability, and this is also stable. All right. So that's where we will stop with that. So I want to quickly touch supercritical bifurcation, pitchfork bifurcation. Actually, subcritical. We just finished supercritical. So subcritical, pitchfork bifurcation. Similar to the supercritical. So the normal form is a x dot equals ax plus bx cubed, where b is a constant greater than 0. And again, we can just think of it as ax plus x cubed, okay, if you divide through a. Okay, so if you do the same thing that we did, and we did for the first example, so I'm gonna do, let's say, example 4. That's what I'm gonna call it. Example 4 now. So let's try to rehash our old friend rx minus x squared, but now let's do it rx minus x cubed, but now let's do rx plus x cubed. So if you follow the same steps, follow everything, the same thing that we did, things will just flip in this case. All right, it will just flip. This will now be for r greater than 0. You get this diagram right here. For r equals 0, you still get this, but then for r less than 0, that's what you get. And the bifurcation diagram will change. The bifurcation diagram now will be a little different. You will get something like this. Let's go with green. With that, let's go with blue. And then I'm winging it here, but I think it's going to be right. So let's see. Okay. So this is your x dot. This is your x dot axis. This is your r axis. Let's go with black. So that means that for r less than 0, fixed point, the x equals 0 fixed point is going to be stable, and then it becomes unstable once r gets to 0. And it's unstable the whole of r greater than 0. And then this is also unstable. That's not symmetric enough. I want symmetry. I demand symmetry. I demand symmetry. But now maybe I will now not get it. I'm scared. All right. Well, I don't want to deviate from the first thing I did. Hold on. I'm going to do this first. I'm going to copy, bring it down a little bit, and then demand symmetry again. So, all right, let's see if we can get, well, better than before, but still not too good, but it's okay. All right, so that's the kind of bifurcation we get. The dotted lines are unstable branch, unstable, and this is stable. The solid lines. Same thing here. So let's make this a little thicker. Let's see. Now too thick, but it's okay. All right, so this is stable and the dashed line unstable. Okay. All right. So what do we have? We can discuss this a little bit further. I'm just gonna call it discussion. A little bit of discussion. So in the supercritical case, and the case we looked at was x dot is equal to rx minus x cubed. The cubic term, acts as a stabilizer. Okay? It acts as a restoring force that pulls x back towards 0. So what does that mean? You have the cubic term. If we don't have the cubic term, think about it this way. I'm going to go here. I'm going to erase this. If we don't have the cubic term, if we just have r less than 0, for instance, then we have, let's do this in pink. We're just going to have this for r less than 0. Okay. And then if we have for r greater than 0, we have this, I guess. Okay. All right. No. Let's do this. Sorry. I want to do it. So for r less than 0, if we didn't have x cubed, that's what we get. Yes. And if we didn't have x cubed, for r greater than 0, we will just get this. We'll get that. Okay. So the cubic term allow us to have these two fixed points, stable fixed points, and allow these two fixed points to move towards each other and coalesce at x equal to 0. Okay. And in the case of the subcritical, in the subcritical case, okay, rx plus x squared, the cubic term acts as a destabilizer. All right. Okay. Cubic term. All right. Cubic term acts as a destabilizer. Okay. All right, so let's stop there. We're going to talk more about this maybe in the next video or in class. All right, bye.